Oh, hello everyone, and welcome to another GOAT seminar. Today we have the pleasure of having with us Lluís, who is a PhD student at the University of Charles, and will talk to us about what he will present, which is on eliminating majority illusions.
As you may see here, this project is a project we started 1 year ago, and that will be presented also in AAMAS. But this is like films in cinema, no? Before you send the film to cinemas, you have like a premiere with distinguished guests, in this case you, and there is also some of the actors of the project there, like Foivos. So you can talk at any point if you want to say something. We are not all here. There's Abhiruk, Antonio, Diana, and Samuel that are in Germany, I suppose. No? So I think this is more or less the introduction I wanted to say about how we did this project. So I think we can start now. So first thing I have to do is to explain you what is eliminating illusions problem. So I think it's more or less easy when you see an example. You will have an input, and that is a graph and a labeling with only two colors, in this case blue and gold, and the majority will be blue. From now on, every row that you can see will have two colors, and blue will be the majority. So the idea of the problem is that in this type of settings, there can be some vertex that, for example, in our example, this one, then when you ask this person what is the majority color, this person will say gold, because he looks in his neighborhood and there are more gold than blue, and this person will be under illusion, because the reality is that the majority is blue. So our task is to minimize the changing of colors of some vertices in order that no one is under illusion. So, for example, in our case, we only have to change this color, and now whoever you ask, whatever vertex you go, the neighborhood will be majority blue. So nobody is under illusion. And the solution will only take one labeling. First easy thing that you may remember from now on is that in order to solve this problem, we always be changing gold to blue. There is no reason to change one color, one vertex that was blue to gold. Okay? I think it's more or less reasonable to think that. So this was the problem of eliminating illusions. And now I will talk a little bit of what results have already been done. But the first thing I have to warn you is that most of the results already done, the eliminating illusion process is done by adding or removing edges, which is a different approach from what we have done. In our case, we are relabeling the vertices. In these cases, they are adding or removing edges. So there is some work done, for example, some generalization of the problem, Q majority, in which you allow some fraction of the vertices to be under illusion. So, for example, if Q is a quarter, then you allow 25% of the vertices to be under illusion, and this would not be a problem. So we are working with Q equal to 0. Then there is detection when they give you a graph and you say if there is some labeling that can produce some illusion that has these results. This would also work in our case because they are not trying to eliminating, just to detect it. And there are other generalizations like the illusion, in which you allow, instead of looking a majority, you look for every vertex to have some proportion of vertices of neighborhoods. Like instead of asking the label 1 to be bigger than the label 0, you will count 1/3 of the label to be bigger. So these are some generalizations, but we again our results are with vertex labeling. So they are totally different from the results that you can expect from adding or removing edges. So here you can see the results we have found so far. And I will start with the first two now, but so we will go with polynomial and FPT algorithms from one problem, then some complexity results, NP hard, and finally we will end with the PTAS for planar graph, which is a little bit technical. So for this one, I will just give some hints. So let's start with the two first results, and they come from a different problem that is not that known. So I will state it here. So in this case, total vector domination, it's a little bit different from vector domination than maybe some of you know. But in this case, what you have is, again, one graph, and every vertex has some demand. So this vertex is asking that when you select the set S, this set has two neighborhoods selected. So for example, one solution, again, with an example, it's much more easier. One solution to this problem would be this. So now, whatever you go, if you ask here 2, you can find 3, it's fine. It's just more than 2, okay? So this is total vector domination. And first thing we will do is, given an instance from our problem, go to total vector domination. So
I was just wondering, why is it called vector?
Because technically, you will have the demands as a vector with every.
Okay, it's a vector with one point.
Yeah. I didn't choose the name, so. So imagine we are given some input like this. So now we want to transform this into total vector domination. First thing we can think is just to put more than half to every demand, and this would say that whatever we choose as a set, no vertex will consider that set. All the vertices will consider that set like the majority. But if we go back to the definition of what we were trying to do in eliminating illusions, we do not want like the minimum set that nobody considers that the level blue is the minority, but we want the minimum set from this one. So somehow we have to ensure that these vertices are again relabeled as blue. And this is really easy to do because you can just put some leaves and mark this one. So this forces this one to be selected. So you choose the original vertex and then the other condition satisfies everything. So just with this simple trick, we can take some results from total vector domination. The sad part is that there are not many results from total vector domination. So we can take, for example, these two, polynomial algorithm for trees and FPT algorithm for planar graph, but there is not much else in total vector domination, at least what we have seen so far. But the good part is that I have done a little bit of a spoiler there, because I said no reduction but equivalence, so part of our problems will be fine for total vector domination. So we have to do the equivalence now. We start with one input from total vector domination, and we transform it to this one, which is just a copy with. When you see that this is a square, it's because it's not a leaf, but some path or some structure that just gives this vertex of this color there. So we do that, and now we use this definition of budget in which we add leaves depending on the number that appears as budget. So for example, in the B5, you have demand 1, so it would be 2 times 1 plus 1 minus 3, because it's the degree of the original graph. and this is equal to 0, so you do nothing. But if you go to B1, then you will have 3 minus 4 minus 1. No, you will have, yeah. So you have to add 1 blue leaves. And if instead of minus 1 it's plus 2, like in B6, you add golden leaves. So this way, solving total vector domination will be just doing majority illusion to this graph. So you have both reductions, no? So it's an equivalence. We have already seen two of the two first results and the equivalence with total vector domination. So now we will go for a little bit of complexity. So we will start with these ones. And obviously, if we study the complexity of the problem, first thing to say is it's NP something, in this case, NP hard, and we can do it by set cover. Well, you have an example of how set covers looks. I hope you more or less know how it works. So once you have this instance in which this will be the elements and this will be the sets, to transform this into elimination illusion, it's just to do this. So we add these ones in order for blue to be the majority, and in every blue we add d minus 1 leaves. So every vertex here is under illusion by 1. So now if you want to remove all the illusions, you need to relabel somehow these vertices such that touches everyone, which is set cover. And this gives us NP hard and W2. So even for bipartite graph, but we can go a little bit further, because in this case, if we go for this problem, planar monotone trisad, which is really restrictive, no? It's trisad, but it has to be planar, and you can only have clauses like this, either everyone not negated or everyone negated. So this generates a graph that has maximum degree 5, and it's also bipartite. And the only way to find a valid labeling with the number of variables, the size of the number of variables, is that this vertex is always under illusion by 1, so you have to choose one of the two. So one would be true, the other would be false. And this vertex is under illusion by 1, so you have to choose one of the clauses that appear. So if you are able to find a relabeling of size and number of variables, then you will have satisfiability for planar. And this gives us also an NP hard, even for bipartite, planar, maximum degree 5 graphs, which is quite a restrictive classification. So once we know that it's NP something, then we try parameterized algorithms. And the positive result, so we have two negatives, now we go back to the positive results, is that we can find a parameterized algorithm with vertex cover. So the idea is that vertex cover will give us two classes of vertices, one that will be U and the other one is an independent set. So we will use that in order to do an ILP program. So the algorithm will work like that. Once we have the vertex cover, then we have we try to find an optimal relabeling for just for the U vertices. This is two BC possibilities, and this relabeling that will solve all the vertices on I, because I are only attached to U vertices, and we find an optimal relabeling there. Then we split I in different twin vertices classes. We also know that these classes will not be a big number of classes, and then we can apply our ILP, which will look like this. And now maybe I should explain a little bit what those letters mean. But I have the syllabus here. So the idea is that xi are the vertices that will be labeled as 1 at the end of our program. And then we want xi to be less than ai, which are the vertices that were labeled at the beginning of our solution. So this just ensures that we will not label more ones than we had at the beginning. And then the second condition just ensures that no vertex in U will be under illusion, because NU are the neighborhoods in U that are labeled as 1, and I it's just if it's adjacent or not to this set of vertices. So this condition ensures that U will not be under illusion. This other one ensures that you will not relabel more things that you had before. And as we have solved already I, we have the FPT algorithm. Okay. So this was a positive result. We go back to the negative results. It's happiness doesn't last long in this case. So we will show X and LP hard. I don't know if you are familiarized with this class of complexity. If not, the thing that you should take into account is that if you show that it's X and LP hard, then you can say that it's WT hard for any T. And we will do it with this other problem. I don't know if you have seen it before, minimum, maximum out degree. I have put an example here, but I didn't remember to put weighted edges. So imagine that every edge is weight 1, and you want to make an orientation of this graph such that no vertex has more than 2 out degrees. No? So for example, one solution would be something like this. So this is what we want to solve. So it's a little bit strange that eliminating illusions can be used in something like this, because this is orienting edges and eliminating illusions seems not that clear. But in order to do that, we will introduce this tool, the chessboard. So a chessboard of size 3 will be something like, we'll start with a grid of 2 times 2 sides of the chessboard, and then we will add these switches. So now in this case, blue is the majority, and every vertex that is in the grid and blue is under illusion by 1. So you have either to take this or the other yellow vertex to relabel in order to bring this one out of illusion. So there are only 2 optimal solutions. One would be this, relabeling the dark blue ones, or this one. Okay? So this is our chessboard tool. So now imagine that we have an edge of the MMO problem with weight 3. We will do the following. So we transform this into a chessboard, and now we have these 2 possible solutions that I told you before. So if the solution is like this, then we will say that the orientation of the edge is from B to U, and if it's like this, the other way. So how does this help us to solve the MMO problem? Here we use the observation. So the idea is that we need the out degree to be less than R, but this is the same to say that the in degree has to be bigger than that. So what we will do is to add leads to each vertex in order that the vertex is under illusion by D minus R. And then the way to solve it will be to bring as many blues as D minus R. So the weight will have to be, the integrity will have to be the integrity. So by this, we have transformed our MMO problem into an eliminating illusion problem. So we have the result of X and LP. And this brings little hope for complexity. So we have to go for next attempt to deal with this problem, that is approximation, polynomial time approximation scheme, PTAS. the idea from now on, as there are not more drawings, these things will be more like ideas and not going extremely into details. But I hope you will get the insight of what we did. So the idea is that we will decompose our planar graph into layers. Then we will solve a subproblem for each layer, and we will try to merge the solutions so we have this approximation bound. So to do the layering, we will use Baker's technique, and to solve the subproblem, we will have to find a fast algorithm to solve these subproblems. But before, we have to introduce what the subproblem will be. So subset eliminating illusion is exactly the same as eliminating illusion, but now we have the set S in our definition. That is just telling us that we only want to eliminate illusions of set S. Whatever happens outside set S, we don't care. So, and obviously it's a generalization of the other problem, no? Because if you put S to be equal to B, then you have the original problem. So this type of this problem, we have find this theorem for it. So we have shown that we can find an FPT algorithm parameterized by treewidth and a maximum demand, which the demand is explained here, but is how many vertices do you have to change from the neighborhood of the vertices that are under illusion in the input. And we can find how to find this algorithm. Well, it's done with, as it is treewidth, we have the decomposition. Then we enter this definition of dt. It's the remaining demand, so it's a number of neighbors that can still be relabeled. And then we use dynamic programming. So we define this table in which we are counting the minimum number of relabelings such that we satisfy these four properties. And W are empty set will be the minimum number of relabelings of the total graph with our set. So here I have more technical details, but the key thing is that you can do this, you can compute this table in this running time. And even though it's a little bit ugly, you just need to see that it only depends on treewidth and the demand. So we are sort of safe. Now, there is more technical details here, but I don't know how much time. Okay. Well, this is just if we have our nice tree decomposition, then if we have a leaf node, it will be empty, so we can go with 0. Then the introduce node, if the remaining relabelings that we can do is less than what we need in order to bring out this vertex from illusion, then we cannot solve it, so infinity. And then you have these two cases depending on if the vertex that is added is already relabeled or not. And the forget node, so if we forget one node, we have to be sure that this node has been solved, so we need that the demand for B is 0, and it has these things. And the join node is much more technical, so I couldn't summarize it here, but more or less the idea, you should be convinced now, more or less. So once we realize that we can solve this subproblem in fast enough time, the idea of the PTAS is just we get the input and a planar graph with its labeling and some epsilon. Then we produce this K for some more technical things there. And the important thing is that if we make the layers of a K outer planar graph, then we have a bounded treewidth. So this means that we can go fast with our subset eliminating illusions problem. we solve this for all the layers, and then there is a clever way to merge them back and produce this optimal solution approximation. So our last result, this approximation, would be that for all epsilon we can find some approximation depending only on epsilon. And this was all the results we had, I think. So to summarize and to remember, we have seen that the problem is NP hard, even for bipartite graphs, even for bipartite with maximum degree 5 and planar graph. We have also seen this XNLP class. And we have some FPT and PTAS methods for solving the problem, and equivalence with the total vector domination that should allow us to translate some of the results from there to eliminating illusions, and from eliminating illusions to total vector domination. So this is what we have done. Probably in the future we can also explore some heuristic algorithms, maybe, or approximations. Probably in this case, maybe we can argue that the labeling process is something submodular, and then you can try to find some approximation from that. And there is also the applications that more or less are obvious from this type of problems of two opinions and this type of things. So misinformation, control, digital marketing. But so I think from me that's all. So thank you for your attention.
Thank you, Lluís. Is there any questions that you?
So I'd like to ask for this treewidth algorithm, you require that your demands are not too big. So is that like a justified requirement, or is it hard if you don't require that?
Well, the demand it's a lower bound of the solution size, so you can take it as the bound is the solution size, and you would have an XP algorithm.
Yeah, but
yeah,
it's I'm not sure now about this XNLP hardness, but is it kind of matching to show that is it? Oh. Is it kind of matching to show that you cannot have a better algorithm on treewidth?
I'm not familiar with that. So.
The XNLP hardness we had was for pathwidth.
Okay.
Yeah.
So basically, there is no treewidth.
Okay.
The algorithm. Any other questions?
So, did you consider the case where you have multiple colors, like more than two?
Not for the moment. It should be future work.
Any other questions? Yes? Okay, so if not, let's thank the speaker again.